Welcome to the session. Greeting of the day. In today's class, we'll continue with the non-destructive testing for one of the important testing method is nothing but a magnetic particle testing. In previous classes, we have seen the various test procedures that we are following now in the magnetic particle testing. So we have earlier simply we have classified this magnetic particle testing in terms of surface detection crack, and also some other things are subsurface types of testing cracks are also available. So in this topmost 8 methods, we are as of now concentrating on this magnetic particle testing method. Here in the magnetic particle testing procedures, we are seeing some 5 steps involved there. It's nothing but pre-cleanings and insertion of magnetic field and the application of magnetic particles, then inspections, 4 over. And last we have the fifth point as post-cleaning and demagnetization. We want to see about this demagnetization, very important factor. As we are using a ferromagnetic material, this ferromagnetic material is already in the magnetizing properties there, but it is not oriented. Each one it is in the various direction, and therefore we will not get a strong magnetic field. This is what we have expressed in the procedure itself. Therefore, we are using a separate magnetic field to attract all these non-oriented fields into one direction. In such a way, it will be helpful to identify the crack. So, in such cases, when the magnetic field artificially applied magnetic field, when it is terminated, this ferromagnetic material will have a residual magnetic field which stores back on the material. Therefore, it should be demagnetized in such a way it will not affect the secondary other processes or otherwise in the in-service treatments also. So with this introduction, we want to see about what are the types of demagnetization. What are the various types of demagnetization also we have seen. This is the last step. So initially you see a created magnetic flux for inspection that have to be destroyed, because we have created a magnetic field by applying a probe, and we have created the passing the current, and magnetic field is created perpendicular to it. Now this created magnetic flux is to be destroyed, otherwise it will create a residual magnetic field. So we understand why it is created. If it is residual is there, for example, if I wanted to do some a cutting treatment or a machining treatment and have a tool and I have a workpiece in hand, I'm taking nearer to it. Instead of cutting process, it will attract somewhere and it will stuck together and the process will not take place. Therefore, we have to be serious here that every process after that we have to go for demagnetization. Therefore, it will not attract further, or otherwise it will be stationary for the specific work. Therefore, I am dividing into 2 categories of demagnetization methods, and they are number 1 is a heating method, and number 2 is a electrical method. One by one we will see. If we are completing this, it will be we will entirely understand that what is demagnetization, various methods. See, number 1, a heating method. It is general. You see, we have learned in the iron carbide phase diagram in metallurgy that iron specimen when it is heated above the cubic temperature or above the critical temperature, the BCC is going to convert into FCC. This we know, we have studied. The same formula we are going to use for this also. So it means we are heating the specimen above the cubic temperature in such a way it loses its magnetizing property. You see, that's what. A random orientation of the magnetic domains can be achieved. It means already it is in random, when it is kept probe, it become a oriented one, and we are trying to make it again as a randomly oriented. So how we are doing? Already the specimen is available here, and we are keeping the probe. It is going to become as it is in a one direction orientation. All the specimens. This diagram we have seen. It means various after solidification grains are formed. So each grains are in many directions. So when it is magnetized, all become in uniform direction. So it become in the uniform direction, maybe in the same. So likewise it is going to convert in the one direction. So that is what our interest also. Then only it become very stronger. Now we are going to heat it. It means above the Curie temperature, it loses its property. Then obviously all these are not in the uniform direction. It will become randomly converted to random orientation. It will become this direction. It will become this direction. Something it will become other direction. So the orientation is going to change. That is our interest also. That is what we are trying to do. So the random orientation of the magnetic field can be achieved effectively by heating a specimen. Heating the metal above the Curie temperature, above the Curie temperature of the specimen. So maybe iron 723 or any other small every material it changes. When a part is heated above its Curie temperature, it loses its magnetic property. You see, it loses its magnetic property. When it is cooled back downwards from the higher Curie temperature, it will go through the reverse transformation and it will contain no residual magnetic field. But its actual paramagnetic, what are the properties of the specimen, it is achieved. But what we applied there, it is not residue back, it is going out. The material should also be placed with a long axis in an east-west orientation to avoid any influence of Earth's magnetic field. So there is some other side effects also that is also to be avoided. You see, I have given here a few examples, a few Curie temperatures for every samples. Okay. For iron, it is around 770 degrees centigrade. It's around 770 degrees centigrade. And for steel, it is around 880. It is for fluorine, it is for combination of iron, carbon, steel. For nickel, it is a 358, and for cobalt, it is 1121. All it belongs to a Curie temperature. So we are going to heat in such a way. So just this is a pictorial representation to remember how we are understanding this heating method. So when we are heating up to this point, it is going to lose. Therefore, the residual magnetic fields are moved out. That is what we need. Now I am coming to the second method. Second method of electrical method. We have seen heating. At the same time, you see, we have applied this current perpendicular in such a way, the magnetic field generated perpendicular to the current. Now what we have to do for demagnetization, again reverse current we have to supply. If already current has been supplied in one direction, the reverse direction we are supplying the current. It can be useful to make the magnetic field which is generated perpendicular. Now again the perpendicular will become like this. So automatically it is converting directions. So that is also I am using AC current. AC current is a sinusoidal. Once it supplies in the positive cycle, again it supplies in the negative cycle. Once it goes in this direction, again it goes in the other direction. Therefore, automatically the reversing process takes place. Therefore, it will be much more helpful to demagnetize and also much more useful to this reversing process. These things will happen. So that is what I did here. Subjecting the specimen to reversing and decreasing the magnetic field. That is what we are doing by supplying the electrical current. That is also AC current. Returns the dipoles to a nearly random orientation, because you see here in the AC current supply, it will be like this: a positive, negative, positive, negative. So positive, negative, it will be like this. Therefore, here it will be in one direction, other direction, one direction, and other direction. Therefore, automatically the magnetic field also get reversed. At the same time, this magnetism also reversing, the orientation also reversing. Therefore, we won't get a strong magnetic field. Then how we have achieved previously by using rectifiers and filters. We have made rectifiers to make this half of the negative cycle to upward. Therefore, we received in such a way. Therefore, we received in such a way. And we have applied filters. This is rectifiers. When we applied filters, therefore, we achieved a as like straight path like a DC supply. That is how we trying to do. But even though normal AC current we can supply in such a way, it can be useful for demagnetization treatments. See, to do demagnetizations apart, what I am doing, AC magnetic field, AC a magnetic field is needed, which is to be greater than that of the current what it is supplied. Magnetic field used for the magnetizing a part. So in case I am using for magnetization of 100 amps, let us assume of when I am using for 100 amps, then I have to use more than that of at least 120 amps of current. So that will be make a sense of higher current, higher magnetic field. That is also in the opposite reverse direction, makes a a random orientation. In such a way, it will be easier to demagnetize. So AC current we are supplying, and then after it is supplying, therefore a material loses its magnetizing property. This red color I am reading. A material loses its magnetizing property as AC changes its direction for every half cycle. That's what I have drawn here. For every half cycle, it changes its cycle. One it is positive, one is negative. One is positive, one is negative. And so this distributes the molecular alignment in opposite random orientations, resulting in the demagnetizations. And after that, after demagnetization, the supplied current, what you have to do? Slowly reduce to normally to the zero. As it is, then the leaving the part the demagnetized conditions. So it is also a good method and also easier. Some other methods are there in general. Normally, we have in the classifications I have given, one is the heating method, one is the electrical method. And some other methods also we can see. You see here, I have used here a simple method. It means in this image you see this option of graph. When I am taking two magnets nearer, when I am taking two magnets north and north pole and south pole, obviously it is going to repel. It means a mutual force always or repels, and then it attracts opposite forces. Therefore, by doing so, this repulsion action makes the magnetic field what is present there to reduce. So this is also one of the option that we can able to try to demagnetize. Magnetization should reduce. That's what we need. Otherwise, what we can do in the magnetizing or demagnetization, I'm scratching something. We have played this game in our young ages. So school boys. So we will take a paper or we will take a pen. We have kept the magnets over there. Under that understand some particles will be attracted. Likewise, when a material is there, we are scratching a permanent magnet over the specimen. These zones will become magnetizing in nature. So that is how we can try demagnetization process also, opposite reactions doing process. We have ended with these types of demagnetization treatment. It means we have up to now we have seen demagnetization, what it is and why it is we are doing, and what are they types: heating method, electrical method. Okay, somehow the other scratching methods also, keeping nearby, and a repulsion force also. Now How to identify this magnetic is stopped or how it is demagnetized? We should know. Therefore, I'm using a two equipment a component to calibrate or standardize. So standardization calibration we can do by this using magnetic field indicators. So that's what I have given a heading, a magnetic field indicator. You see, I am dividing into two categories of QQI, quantitative quality indicator. It's nothing but indicator to find the quality, to calibrate if it is correct method. Otherwise, we will get the doubts whether the crack is available, present or not present. Whether the process done, the supplied current to make the proper this quantum of magnetic field. The quantum of magnetic field only receives or attracts the particles what we are pouring over there. Therefore, we will get a doubt in doing inspection whether it is a method is done is correct or not correct. Therefore, what we have to do, we need a calibration setup to calibrate. Yes, it is correct. Then whether it attracts or not attracts. If it is not attracted, no crack, no discontinuity is present. If it is attracted, yes, there's a crack. We can justify. So first point we need is to identify whether it is doing a calibrated, it is standard, it is correct or wrong. Therefore, we have two components there. One is a quantitative quality indicator, and then one is a pi gauge. Two equipments are there. One by one, we will go ahead and we will see. Quantitative quality indicator. The quantitative quality indicator or artificial flaw of standards is often preferred method of assuring a proper magnetic field direction and adequate field strength. It is used in the wet methods only. You see, this point is important, please remember. It is used in the wet methods only. You see, we are using a strip of small strip of ferromagnetic material, a very thin 0.00, it is written given here. See, 0.005, 0.02, 0.1 mm of thickness. What I am trying to do here, I am placing this thin 0.1 mm of sheet over the specimen here, over the specimen. What happens? It is sticking over the specimen where we are going to do inspection. Where we are going to do inspection. Then what happens? Then what happens after doing such a placements? I wanted to pass through the liquid, which means wet particles. You see, the color changed slightly. In this first one, in this first GIF, it is playing. Here they are placing the strip. In the second one, after placing the same specimen for inspection purpose to find the discontinuity, they are placing in a horizontal setup, a longitudinal horizontal machine setup. This also we have seen types there, horizontal machine setup. Then after that, they are supplying a liquid. This is the third one. You see here, third one. They are supplying the liquid. It means wet particles, wet substantial particles. When it is applied, these water particles are also absorbed by the strip. It means the small thin sheet, 1 mm sheet, and also it is floating over the every specimen. Now, if on the sheet we have a symbol of plus, that is what it is given here. You see in the left side image here. This image you see here we have a circle. We have a circle on the strip, or maybe a plus sign. Or maybe a plus sign. What happens? In which direction the magnetic field is available? When the current is supplied in the thumb direction, magnetic field will be in the finger direction. That is what here. So, in which direction the magnetic field is available? And then perpendicular to the magnetic field, crack can be observed or detected. It should not be parallel to the magnetic field, then it is non-detectable. So we can understand in which direction we are doing the magnetizing. in which direction the current is done, which direction it is stronger, field is stronger. If it is stronger, it is easily able to identify the crack perpendicular to it strongly. There won't be missing of the discontinuities. It is a good one. We can easily qualitative the cracks. How many cracks are available in the horizontal direction? How many cracks are available in the vertical direction? So we need some calibrations and standards. Therefore, that strip does that job. See that is what I have written here also. A QQI is a thin strip of a 0.05 or 0.1 mm thick of ASI 1005 steel with a specific patterns. The patterns may be the circular one or maybe the plus sign. That is what here it is in the image also it is given. The QQI is placed directly on the surface with the edged side facing the surface, and it is usually fixed to the surface using a tape. Yes, in the image we have seen we are sticking out through the tape. Then the component is then magnetized and particles are applied. Yes, we are applying the current and the liquid suspendable magnetic particles are poured over the specimen which we need to do inspection. When the field strength is adequate, the particles will adhere to the engraved patterns and provide information about the field direction. What it means, you see, on the liquid water particles, liquid magnetic particles are there. On the liquid magnetic particles are there. In which direction we are supplying current, on the same direction, it will be particles will be attracted because magnetic perpendicular to the magnetic field. So according to the direction, on the engraved pattern is engraved on the plus sign, maybe in the horizontal direction or maybe in the vertical direction. So on the any direction perpendicular to the magnetic field, the particles which we are thrown over there have to form. If the magnetic field is in this direction, magnetic field is in this direction, the particles which are thrown over there ought to be perpendicular in this direction. So plus, we are forming plus here. We are forming a plus here. So accordingly, in any engraved patterns, it will settle down because it is like a crack. It is like a gap. It's not floating. It is settling down there and provide our field information where it is perpendicular direction, horizontal direction. It provides the information. That's how we can able to identify. See in this picture, second picture, bottom below one, we have supplied the liquid on the engraved plate. We have supplied the water suspendable ferromantic material. Particles are sprayed over there and inspected through a black light, a UV light. Therefore, it is green in color, and the specimen looks green. Here, the specimen is looking green on the second image. Now we go to this also. See in the third image, you see the third one. First one they are sticking out. In the first one they are sticking out, and in the second one, you see. The second one they are holding on the specimen on the equipment, and in the third one, they are supplying the liquid. They are supplying the liquid one over the other. Supplying the liquid, which water suspendable particles are there. Therefore, that water is poured over there. This is how we can continue. Now let us assume if during calibration process, if we are not possible, I'm talking about this 1, 2, 3, 4th image. If we see here the plus sign to be properly visible when we are doing supplying the current in any direction. So the plus sign should be visible in which direction we are supplying the current, on the direction the line to be formed. When you are seeing this image, a line is not properly visible. Therefore, we are increasing the current. Adequate current is supplied over the specimen. It is also we are understanding ourselves what is the calibrated current to provide adequate strength of a field, that we understand and that we are supplying. That is what in this first third image, 1, 2, 3, 4th image. On the 4th image, it is not adequately visible there. Therefore, we are supplying a more current. We are supplying a 4th image. We are supplying a more current here, and then after supplying a required current, you can see, and again we are seeing through the black light. signs are visible. Therefore, you understand it is here in the image it is 0.14, but in the second image you see here 0.79 amps. In the left side fourth image here, here in this image, it is current is shown in the image you see in the GIF file. It is 0.14 when we are adjusting, but at the same similar nearby picture you see in this 0.79 we have adjusted, we have calibrated and standardizing. This is the required current needed to form a strengthened field. In such a way cracks can be, discontinuities can be identified. So that is how it is easier to do. Now in the same sample, this is what the inspection, this is what fixed, and we are doing inspection. So here in the sample you see, on the engraved plus pattern, the sign is in horizontal direction. You see clearly, sign is in the horizontal direction. It looks better than that of others. Therefore, the cracks which are all in the horizontal path can be detected easily. You see there is a crack. Crack is available at this point. Below the strip, crack is available at this point. Crack is available here. So at this point you see crack is available here below this plus sign. So it is that is how we can able to understand by using a quantitative quality indicator. So this is about one of the important factor. Next we come upon to understanding about the pi gauge. It is one of the important thing. The pi gauge is a disc of a highly permeable material divided into 4, 6, 8 sections. So 4, 6 and 8 sections by non-ferromagnetic material. The sections are furnace brazed and copper plated, which is a good attractive material, a good conductive material also. The division serves as artificial defects that radiate out in the different direction from the center. You see, here we have in the image, in all direction we have the artificially created strips or cracks, like we can consider engraves. So multi-direction. So 1 to 1 it is angled is 45. 1 to 1 its angled is 45, and totally some 90 degrees also found there. After the particles are applied and the excesses are removed, the indications provide the inspector the orientation of the magnetic field. You see here in this small GIF file I have added here, you see in the first image, left side first one, this image, a magnetic field box, a magnetic field probe is we are keeping over the specimen and supplying the current. As we have seen there in the electrical strip method, QQI, fault indicator, here also in the pi gauge, we have a star at the symbol, engraved star. In that, where the flux lines are available or where the magnetic field is generated, where it is perpendicular, accordingly it crosses the strip lines. As when we are keeping immediately, you see this point, it is immediately it is fluctuating. This point you see clearly, it runs on again. When we are keeping, it is perpendicular lines are not formed. It means this line is not there at center line, left to right is not there, east to west, center line is not formed. Other lines are stronger. It shows you the perpendicular lines of the passing through of the current. So that is how we easily identify. This is what the image I have showing you in a close-up view. So this one, you see, the center line is not available because we are supplying the current here from here to here. So it is something happening there. We understand that the point is not attracted. Remaining perpendicular points are attracted there. So it is one of the easy a calibrating equipment, a pi gauge, which is useful to understand the weldments or casting things. Pi gauges are mainly used on flat surfaces such as weldments or steel castings where the dry powder is used. You see, previously we used the wet method for the previous type for quality indicators. We used the wet method. For the same here, we are using a dry method. This package is not recommended for precision parts with the complex shapes or for wet method applications. It is only for dry method applications, not for the wet methods. Or for providing a field magnitude. The gauge should be demagnetized every time. Somehow we are trying to demagnetize also these things. So that is how the pi gauges are used. So measuring magnetic fields. One is a field indicator, one is a Hall effect meter. You see one by one. This is one wonderful example to identify whether it is demagnetized or not demagnetized. It's a pocket gauge pocket gadget. You can keep in the pocket and you can take. There some magnets will be there inside kept. Accordingly, it will the knob will be moved here and there. The field indicators are small mechanical devices that utilizes a soft iron wand that deflects by a magnetic field. A wand is attached to a needle that rotates and moves the pointer for a scale. So here we have a scale. It moves here and there. Accordingly, we can identify that it is in magnetic condition, it is in demagnetized state. The field indicators can be adjusted and calibrated so that quantitative information can be achieved. Yes, quantitative is nothing but a magnetized or not magnetized. Measurement range of field indicators is usually small due to emission of devices ranging from 20 to minus 20 kHz, because these field indicators give very minute information only, not much more large informations. We are not possible to getting such more information also. Therefore, what we can do, this small micro gauge information will be helpful to identify a residual magnetic field. Residual magnetic field is a very smaller quantity, not a larger one. It is a very smaller quantity. Therefore, it is best suited for measuring the residual magnetic field, because these pocket gauges are useful to measure only a smaller magnetic field, not a larger one. We are not using this larger one. It is useful to measure only a smaller one. Therefore, this smaller one is best suited to understand the residual magnetic field. This is how a small experiment I am trying to do here. See, in these three images, they are using, in the first image you see they are using a magnetic field indicator in such a way the needle is moving left to right and right to left, something it is shaking, in such a way you understand. Therefore, in the first image you see, the top first image, when we are supplying the specimen as parallel to the current, there is no change in the magnetic field. It is not demagnetized. But at the same time, on the last image, below image, we are sending perpendicular, hands are perpendicular. We are sending perpendicular to the supply. Then it becomes demagnetized. It's randomly oriented, and therefore it is demagnetized. So that is also, it is indicated in the field indicator. You see the first image, they are taken and saying it is indicator's needle is moving. But at the same time, on the second image you see, they are sending perpendicular, therefore it is demagnetized. Now you see, they are sending perpendicular to the coil, therefore it is demagnetized. And now when it is measured through field indicator, the needles are not moving. The second one. That is how we better understand this field indicator. A Hall effect meter. A Hall effect meter is an electronic device that provides a digital readout of a magnetic field strength in gauges or Tesla units. The emitter uses a very small conductor or semiconductor element at the tip of the probe. Electric current is passed through the conductor and a magnetic field, a force is exerted on a moving electrons which tends to push them to one side of the conductor. We are using some digital formats to check whether we are touching methods to understand whether it is magnetic field is generated or it is demagnetized. So portable power supplies, these things we have already seen in the supply probe methods, two hand taking probes or one hand taking probes or yoke methods, electromagnetic yoke methods. These are all things we have seen. Just for image purposes I have included here. It's also one of the equipment we are using for generation of the current in such a way, generation of the magnetic field. So thank you for joining for this magnetic field session. We have done nearly 7 to 8 lectures. With respect to that, we conclude this magnetic particle testing module. And then maybe we will meet you next in the next module. Thank you for joining.